So, see, my slides are visible. My slide is visible to you, everyone, please.
Yes, sir. Yes, sir.
Okay, okay. Thank you. So, yeah, is it visible now clearly? Okay.
Yes, sir. Yes, sir.
Okay.
Please.
Okay. Thank you. Good afternoon to everyone. So, as you see, already he has introduced myself. I'm a man of number theory. Actually, I'm researcher in number theory, and I'm especially working on some recurrent sequence. My talk is not based on the deep research here. Just I want to say that how the recurrent sequences are useful, or uh, actually what research are going on involving these recurrent sequences, and I will give some idea about that in my talk here. Before that, as you are celebrating International Mathematics Day, I congratulate you all, or my best wishes to all of you for International Mathematics Day or Pi Day. And before I start my main topic, recurrent sequence, I would like to tell that there are some sequences or some numbers are there which are very interesting. For fun, I just these are some slides, and you just make it for fun only. So the first slide says that, you see, there are some serious and some funny quotes. So I have collected from the internet, and you have seen, all of you have seen my time. So mathematics is not about numbers, equation, computations, algorithms. It is about understanding. See, another famous mathematician, Sakuntala Devi, her quote is like this: without mathematics, there is nothing you can do. Everything around you is mathematics, everything around you is numbers. This is 4 out of 3 is wrong actually. 3 out of 4 people struggle with mathematics. Everybody understand that. 3 out of 4 people struggle in mathematics. This is also some funny quote. Math may not be teach us how to add love or subtract hat, but it gives us hope that every problem has solutions. Mathematics is this is the famous mathematician George Poloya quote: the mathematics is the cheapest science. Unlike physics or chemistry, it doesn't require any expensive equipments. All one needs, all we need for the head of the snake. So is mathematics at the head of all knowledge. So this is by Vedanga Jyotisha explaining the importance of mathematics among all the sciences. Now, so I would tell one thing here, that we know that any sloka in the ancient Hindu manuscript has more than one meaning. A sloka in the 10th book of Rig Veda appears to be written for praising Lord Indra. You know, the technical, it starts from Pa. Then Yadhastaka, Astaka, matlab 8. So it's starting from Y and to actually 8, 1 to 8. Start from Y, Y, Ya, and it is 1 to 8. And the Kya represents 0. Kya, Sunyam. Sunyam means 0, you know. So Kya represents 0. So there is a sloka. This is the sloka here. Gopi bhagya madhubrataha srunga sodadhi savignaha khala jivita sandaraha. So if we put gopi means ga is 3, pa is 1, bha is 4, ya is 1, according to that numerical code, and you will see that it is surprising. You will see that the value is like this: 3.141. Not point actually, we are putting a point there, but the values are 3.141.592 up to, correct, up to 32 decimal places. So even a modern computer cannot find the value of pi up to, I think, 22 or 20 decimal places, up to 16 digit decimal places maybe. But this sloka, if we put that numerical codes there, we are getting this 32. This is a strange thing here for pi. Okay. Now I will tell some interesting numbers which are related to my topic. One is called the triangular number. You see, the meaning of triangular number is a number which is in the form of n into n plus 1 by 2. You see, n into n plus 1 by 2. Any number which is in the form of n into n plus 1 by 2 is a triangular number. For example, if say 6 is a triangular number, because we can write 6 as 2 into 3 by 2. 10 is a triangular number, 15 is a triangular number because it can be written in the form of n into n plus 1 by 2. Why it is called triangular number? Because it represents a triangle. Though you see the first 1 is a triangular number here. This 1, because we say it is a point triangle here. It forms a triangle over it. Next is 3 is a triangle because 3 can be written as 2 into 3 by 2. N into n plus 1 by 2. So 3 represent a triangle. The another one you see, the next one is 6 represent a triangle. This is 3, this is 2, and this is 1. Then 10, fourth one is 10. The first triangular number you can say it is 1. Second triangular number you can say it is 3. The third triangular number we can say it is 6. The fourth one we can say it is what? 10. And what about the fifth one? So anyone can find here. How we are getting, you see. This is 4 plus 3 plus 2 plus 1. It is actually the sum of n into n plus 1 by 2, actually the sum of the first n natural numbers. So that is the formula here, n into n plus 1 by 2. Therefore, T5 is actually, we can find T5 as 5 into 6 by 2. That is 15 is the fifth triangular number. So in that way, we can find the other triangular numbers. Am I audible? Am I audible? Am I audible?
Yes, sir.
Okay.
Yes, sir.
Thank you. Okay, now, next one is, there is another formula to know that a natural number n is a triangular number or not. So any natural number n is said to be a triangular number if 8n plus 1 is a perfect square, So, because we have already seen that 1 is a triangular number, so you can put here 8 into 1 plus 1 is 9, and 9 is 3 square is a perfect square. Now 8 3 is a 24, 24 plus 1 is 25, and it is a perfect square. 8 6 is a 48, 48 plus 1 is 49, which is a perfect square. So triangular number is in this form. N is a triangular number if 8n plus 1 is a perfect square. Right? Okay. Now, yes. Now, okay. Now, this is just for fun only. What is a happy and sad number, you see? There is a definition of happy number here. A happy number is defined by the following process. Starting with any positive integer, replace the number by the sum of the square of its digits. So if we consider a positive integer like suppose 15, and you want to verify that this 15 is a happy number or not, then you replace that 15 as 1 square plus 5 square and calculate its value. 1 square is 1 plus 5 square is 25, it gives 26. Then repeat that process. Same process you repeat it until you get 1. If you are getting 1, then you say that your number is a happy number. The starting number, that 15 is a happy number. If you are not getting 1, if you are getting a looping, and you are not getting 1 in that case, we say that is a sad number or unhappy number. I can give one example. You see that. I am giving an example to you. So you see, let us take a number 4. We start with 4. So first is 4 square. 4 square is 16. 4 is replaced by its square of its digit. So 4 square is 16. Then you just repeat the process. 1 square is 1. 6 square is 36. It means 37. So Let us do for 13 first, because first happy, then unhappy. Okay. So if we start with 13, then it is 1 square plus 3 square gives us 10. Then we start with, then we again repeat that process. 1 square plus 0 square gives us 1. Because we are getting 1 here, so 13 is a happy number. But see the 4, number 4. 37. 3 square plus 9 square, that is 9 plus 49 is 58. Then again 5 square plus 9 square, 25 plus 81 is, I think, 25 plus 81 is how much here? 58. 5 square plus 8 square. Okay, no, yes. That is 5 and 6 at 8 to ja? How much here? 106, I think. Huh? 516, 8 to 10. 9 square is 81, na? 25.
So 5 square plus 8 square.
Oh, sorry, 8 square. I'm sorry. 8 square. That is 64. 64, sorry. So 5, 4 is 9, 60, 89. Yeah, sorry, 89. Then 8 square is 64 plus 81. Gives us how much here? 5, 145. Correct? Then again you repeat that process. 1 square plus 4 square plus 5 square gives us what? 1 square is 1 plus 16 plus 25. How much here? 5 square is 25, 5, 6, 5, 11, 12, 2, 42. Yes or no? Then 4 square plus 2 square is how much? 16 plus 4 is 20. Then 2 square plus 0 square is 4. Yes. Now again we see that we start with 4 and now it comes 4. That means we are not getting 1. It creates a loops there. Okay. So in that case, we say that 4 is not a happy number. It is a sad number. So this is the definition here. Okay. Now, okay, sir. So I have already told you that 23 is a happy number or not. Just test it. 23 means 2 square plus 3 square is 13. And we see that it is 1, so it is a happy number. And 4 is not a happy number. It is a sad number. Now this is the some numbers I have taken from 1 to 30. 130, and we see that these are all happy numbers here. Because see the row mark, if we goes on that row mark wise, you will get 1. Ultimately, we will get 1 here. You see, 91, that is 9 square plus 1 square is 82. 8 square plus 2 square is 68. 6 square plus 8 square is 100. Then 1 square plus 0 square plus 0 square is 1. So you can go 79, then we'll go like this. We'll get 1. So all the numbers, if we go on in that process, we are getting 1. So they are all, on the screen, the numbers which are shown to you, they are all happy numbers. Yes. Any problem? Any problem? Anybody? No? Okay. Now, the very interesting thing is the sad number one. You see the picture of sad number. It's a very interesting one. Looks very nice, you see. All the number on the screens, they are sad number. If you go from any numbers here, you will see that it is either goes to 89 or 145 or 42 or 20 or 16 or 37 or 58. So in that case, this forms a cycle there. So when a cycle form, it means we will not get 1 in that case. So these are all unhappy numbers. Okay. Now, I would like to tell this number because this is related to pi, you know. This is the first 6 digit after decimal point, 3.142857. And number theorist find some interesting properties of this 142857. So there, just for fun, you just see that if we multiply this number 142857 with 1 to 6, the number we are getting on the right hand side, you mark it, they all contain the same digit 1428557. This is one interesting observations. If I multiply that 142857 with 1 to 6, not 7, 8, and 9, okay, 1 to 6 only, so we are getting 142857. And another interesting observations for this number is like this, you see. So if we arrange this number in row wise and column wise, and add row wise also and column wise also, and you will find that sum, row wise sum and column wise sum is same, that is 27. This is also one interesting observation for this particular number, and this particular number has importance because it is the first 6 digit after after decimal of the pi numbers. Okay. Now this is okay, sorry, 1 minute please. Okay. Now another interesting observations are there that if we add the first 3 numbers 142857, first 3 number with okay, the numbers we are getting here in the right hand sides, if we add the first 3 with the last 3, every you see this is 999. This is also one very interesting observations. And if we digits, second 2 digits, third and fourth digit and fifth and sixth digit, the value is 99. And another one is if we square it, it is not 2 actually, it is square it. If we square it, we get these values, 142857 ko agar up square karenge, then we are getting this 204081222449, and the sum of the first 5 digit with the last 6 digit gives us the number itself, 142857. So these are some interesting observations of this numbers 14285. So now I will come to my topic. So that is the recurrent sequences and an overview or at a glance. Okay. So what is a recurrent sequences? A recurrent sequence means if we consider a sequence, any sequence here an, a recurrent sequence means its nth term is an, can be expressed as any relations between its previous terms. Okay, previous term means an minus 1, an minus 2, an minus 3, and so on. So if its nth terms are expressed in terms of its previous terms, then that type of relations are called the recurrent relations. The relations like differential equation, this is sometimes called as difference equation also. Recurrent sequences are sometimes called as difference equation also. So like differential equations, this difference equation or recurrent sequences is characterized as either homogeneous or non-homogeneous one. Homogeneous recurrent sequence, like what is a homogeneous recurrent relations? So any recurrent relation is said to be homogeneous if every terms of that recurrent relations contain a term of a sequence. Every term, every term of that recurrent relation contain a term of a sequence. For example, I'm giving, suppose I will take this an is equal to an minus 2 plus an minus 4, say. You see, this is a recurrence relations. And this recurrence relation is homogeneous because every terms, there are 3 terms here, contain the term of a sequence. But if I add a number here, suppose if I add a number n here, and value n here, then what happens? N is not a term of this sequence. So this term does not contain a term of a sequence, so it is a non-homogeneous one. So for homogeneous difference equation, there are methods, you can read from the book, there are methods in order to find the solutions of the recurrent sequence. there will be a characteristic equations. If we solve the characteristic equations, we get some roots, then we will find the solutions there. There are methods here. So I'm not going details that. So among all the recurrent sequences, what we have read or we know, the most fascinating number sequence and most celebrated number sequence I can say is the Fibonacci number sequence, which was invented by Leonardo Pisa in 1202 in his book Liber Abaci. Actually, that was a problem posed by Fibonacci in that book, and that problem is the famous rabbit problem. So what is that rabbit problem? You see, this is the rabbit problem. You might have know this one Fibonacci sequence, but you see here, suppose there are two newborn rabbits, one male and other one is female. This is one male and this one is female, say. Question is, what was the question? Find the number of rabbits produced in a year if the first one is, there are certain conditions here. Each pair takes 1 month to become mature. एक महीना लेता है mature होने के लिए. Each pair takes 1 month to become mature. And each pair produce a mixed pair. This is also one condition that after maturity पाने के बाद जो पेयर को बार्थ देंगे तो दैट इस प्रोसेस में नहीं मरना चाहिए. All are immortal here. Okay. So what you are getting, you see. Suppose it start from January, in the month of January. So we have one pair. One is male and other is female here. So because it March, now this one become a matured pair. So this is the matured pair here. I am encircling this. And this one is, now this is the original pair. This will gives one mixed pair again. And this new pair will take 1 month to become mature. So now this is the mature pair. So how many pairs in total we have in the month of April? We have 3 pairs. So if you go there like this, you see that the first one is 1, the second one is 1, third one is 2, the fourth one is 3, fifth one is 5, then 8, then 13, then 21, and so on. So
Prashanta sir. Hello.
Hello. I think there is some technical issue. Please wait for some time.
hello, Kalika. Yes. So the first, okay. So this is the Fibonacci sequence, and we start with n is equal to 1, 1 plus 1 plus 1 is 2. And like this, we can generate other Fibonacci numbers also. So any sequence has a generating functions, has a Binet. There are many formulas for Fibonacci numbers. The most useful formula is called the Binet formula. Okay, so I will give some idea about this Binet formula here. So what is the Binet formula? Binet is a mathematician, by his name this formula is named. So it is actually a closed form of this Fibonacci sequence. So how we are getting? You know, this is a homogeneous second order recurrent sequence here. And you know the solutions of this one. The auxiliary equation you can find as alpha square is equal to alpha plus 1. The least one we take as 1. Then it is alpha, then alpha square. This is the auxiliary equations. If you solve it, this is a quadratic equation. It can easily solve. The value is 1. And solving this differential equations, the unknown values are what? B and R here. B and R are unknown values. So this B is called the balancing numbers. R is called the balancer corresponding to the balancing number B. So solving this differential equation, there is a paper. That is a paper here. You can see that paper. You will find how they solve this. Getting B and R, the order pair B and R, and the B is the balancing number, R is the balancer corresponding to the balancing number B. Correct? Now you see. I can show you. These are some examples you see here. B, if you take 6, then 1 to, B is 6, then 1 to 5, left hand side 1 to 5 आएगा, and right hand side में आएगा 6 plus 1 plus 6 plus 2, और भी आगे जा सकता है, but 1 to 5 sum is how much? 15. And right hand side में अगर आप लेंगे 6 plus 1 is 7 plus 6 plus 2 is 8. 7 plus 8 is how much? 15. So now the equation balanced. That's why it is called as balancing number. Left hand side and right hand side is the same now. So when you put B is 6 here in these equations, you will see that 1 to 5 is 6 plus 1 plus 6 plus 2. So 6 is the balancing number and 2 is the balancer corresponding to the balancing number 6. In similar manner, like Fibonacci number, you see Fibonacci number pura pass रहता है. But in balancing number, we see that one is 6, another one is, next one is 35. Serious jump, 35. The next one is 204, you see. मैंने जो प्रॉपर्टी सेटिस्फाई करेगा डिफरेंशियल इक्वेशन का ये नंबर है 6, 35, 204. These are what? Balancing numbers with balancer 2, 14 and 84 respectively. But there is another definition that a square, in that paper it was published, it has been already published, that n is a triangular, n is a balancing number if and only if n square is a triangular number. That is the definition. Any natural number you can test whether it is a balancing number or not. So in order to test that n is a balancing number, we see that whether n square is a triangular number or not. According to the definition, as I told, n square is a triangular number if 8n square plus 1 is a perfect square. So you can verify. From that definition, Diophantine equation definition, 6. Okay. So these are the recurrence relation for balancing numbers. Now another third order recurrence relation. Many third order there, but I have collected some few there because the people are working on this sequence. Mostly this sequence. Perrin sequence like this. Other third order is Fibonacci sequence. Okay. Now I want to tell that what actually peoples are actually doing cryptography, okay, application of number theory, that is a cryptography one. So in elliptic curve, so peoples are doing on Diophantines M tuple. Okay. So this is related to the elliptic curve and cryptography area. And peoples are also doing research in Pillai problems. So I'm giving little bit idea about that because I have the time is running. Just you see, what is a rep digit? You know, rep digit means the digit is repeated like 1 1 2 2 1 1 1 2 2 2. These are all rep digits. Its form is like this in base 10, a into 10 to the power m minus 1 by 9. This is the form of this rep digit here. Okay. Similarly, what is the meaning of concatenation of two rep digits? So if concatenation means आसपास अगर दो रेप डिजिट को रखेंगे आप तो concatenation हो जाएगा AAB, this type of things, concatenation of two rep digits. Now, these are some work in 2000, Florian Luca consider Fibonacci and Lucas sequence and showed that 55 and 11 are the largest rep digits. सबसे बड़ा रेप डिजिट्स है इस सीक्वेंस में, Fibonacci and Lucas sequence में. Then in 2015 they consider the Pell and Pell-Lucas number and show that there are no rep digits beyond 10. Actually one rep digit मैंने सब single digit जितना भी है 1 to 9 they are all treated to be rep digits. बाकी 11, 1 1 then 2 2 they are treated rep digits in the Pell and Pell-Lucas numbers. So these are all papers, they have proved that, and it has been published in various journals. Then Luca and Togbe in 2019, they consider this ln and they showed that Lucas number, they determine all the Lucas number that are sum of two rep digits. Another one is are used in order to find the bounds. Then that is not enough actually. In order to reduce the bound, they are using, the researchers are using certain methods that is called Baker-Davenport method or some algorithm like LLL algorithm. So different methods are there. So these are the methodology which are used in order to prove all these things. Thank you all. So I think I should stop here because it is 6 o'clock now. So if you have any questions, you can please.
Yeah, thank you so much, sir, for first of all mentioning us. And we all enjoyed the beautiful properties of the different type of numbers and recurrent sequences, especially Fibonacci numbers and balancing numbers and ternary sequences also. So now we can take queries. So if anyone have query, then he or she can raise the hand and ask the query. Is there any query from participants?
Yes, ma'am.
Yeah.
Good evening, sir. Thank you for
Yes.
an amazing. Being a student of maths, of course, these series are fascinating. But as we know, number theory application in cryptography, computing, and balancing chemical equations. Could you please explain in brief how it works in cryptography or computing?
You see, yeah. Okay. You see, actually, we are doing basically pure mathematics because this is number theory is a pure mathematics. But some people, even if I also, some few papers I have done in cryptography. Cryptography means what? In image processing, you know what image processing is there. So you
Yes.
want to, yes, you want to blur some image. You can send that image to someone else, and he can decrypt that. Encryption and decryption process. Actually, there
Yeah,
are,
yeah, sir. Sorry to cut you. I
yeah,
understand that, but
yeah,
my question is, I think it's very basic, but I wonder how
yeah.
these series
This
are
series are
composed.
used. Yes. You see, there are certain transformations using the many transformation. I forgot the name. Some transformation are there. I forgot none the name actually. There are some important transformations are there in order to transfer the image in order that they are used in image processing. Okay, so there is a Fibonacci transformations, there is a balancing transformation also. So we can define in that way. Actually, if you see that paper and you will see that how the transformation is defined, and it is also claimed that the Arlon transform, yes, something else. I forgot the name. Yes, Arlon Kate transform, yes, something else. I forgot. So even if the Fibonacci transformation is more reliable than the other transformation that I have already discussed previously, that things that are given in that papers. If you go through that paper, you will find that I cannot describe that in details here, but there are transformations. Fibonacci transformation is there, and the author claimed that his transformation is more reliable transformation than the other transformations so far have been. But you see, after that, some more transformations has also come, and comparisons from the with the Fibonacci transformations, they are the better transformations, right? But I think this kind of work are going on, and modular arithmetic. You might have heard the name modular arithmetic. Hello.
Yes, sir. Yes, sir.
Modular arithmetic. So modular arithmetic has lot of importance in cryptography. Many you can see. Not explain in 5 to 10 minutes. I'm sorry to say, but
So
if
it's
you,
okay.
yeah,
But I got the basic.
Please go through internet and you'll find some papers there, and if you read that, and you'll see there are how the transformations are going on.
Okay, sir.
Or
Thank you
there
so
is.
much.
Thank you.
Any other queries from participants? Okay, so if there are
Ma'am,
not any queries furthermore.
Ma'am, I would like numbers in cryptography or ECC construction.
Yes.
This type of keywords, they may find a lot of papers where there is a
Yeah,
connection
yeah,
between
yeah,
number sequences and cryptography. Yes, sir. Ma'am.
Okay, thank you.
Okay.